has come up is cones. That came up during office hours today, and it came up on Tuesday. So if you guys are graphing a cone for your homework, and let's say you have a cone like this, versus maybe a cone that's facing down. Okay. When you guys read above the cone, what I want you guys to think of that is it means points whose z-coordinates are higher than the ones on the cone. Okay. So what does that mean? That means that there's points on the cone, right? There's a point on the cone with a particular z-coordinate. But for a point to be above the cone, you want another point whose z-coordinate is higher than that one. So would that be inside of the cone, or would it be outside of the cone? Inside. It would be inside of the cone, because, for example, this point here, let's call this A, versus this point B. This point B has a z-coordinate less than it. So this would be below the cone. Right? While this point A, like the cone will keep going. But that point has a z-coordinate bigger than the one on the cone. So you guys see how that point is inside of the cone? Okay? So if the cone's facing up, above the cone really means inside the cone. And below the cone really means what? Outside of the cone. Okay? But when you have the cone facing down, which might happen in some of the problems coming up, when it says above the cone, right? There's a point on the cone, there's a point above the cone, or a point whose z-coordinate is greater, and the point whose z-coordinate is less than. So now if I'm above the cone, is the point inside of the cone or outside of the cone? It's going to be outside of the cone, right? So it's outside. Versus if it's below the cone, notice that now because it's facing down, if it's below, the z-coordinate will have to be less than, so it'll force it to be inside the cone. So this has come up like 2 or 3 times during my office hours these past months. And that's gonna be important for today's discussion. Okay? That kind of maybe clarify some stuff. You're gonna have all kinds of weird stuff. You're gonna have solids that are like inside of a cone, below a sphere, so it'll look like an ice cream, like a little ice cream cone. So if it's like below a sphere, the solid is gonna be the cone with the ice cream on top. Okay? And all kinds of other weird crap that's gonna come up. So just keep that in mind. This is why I was telling you guys, I need you to remember how to at least graph cones, cylinders, quadratic surfaces like paraboloids, ellipsoids, and all that. Those are pretty much the ones we're gonna work with, but you need to have a visual because now the solids are like playing with each other and you need to know, am I finding the volume above the cone, below the sphere? Or am I finding the volume below the cone, below the sphere? Above the XY plane. Like shit's gonna get confusing. Okay? So keep it in mind, keep that in mind, ask me questions as those things come up, and hopefully today's discussion will kind of we're gonna keep doing this stuff in today's discussion. All right, just wanted to bring that up. I had a warm up, but I wanted to cover this instead. Okay? So let's start with 15.6 triple integrals. But before we do that, we're going to look at 2 functions that we've looked at in I think in the previous chapter. Okay. So let's start by considering we're not going to do integration just yet. what does the graph of g of xy equaling 1 minus parentheses x squared plus y squared look like? Okay. What does that graph look like? Chapter 14, I had you guys answer questions like domain, range, all that stuff with this function. But let's see. What is the coordinate that gets outputted for this function? Z. It's the z coordinate, right? So notice that this is just z equaling the square root function here. So if I think of the range of this function, what kind of values will z not be? It will not be greater than 1, and it will not be negative. Okay? It will not be negative because it's a square root, and square roots can't give you something that's negative. Okay? And it's not going to be greater than 1 because this is always going to be 1 minus some amount here. So you're always going to be subtracting from 1. Okay? So notice that this is z equals this, where z is basically squished in between 1, 0, and 1. Cool? Let's do a little bit of algebra here. Let's square both sides. So this is just z squared minus 1 minus x squared plus x squared. But again, we still have this restriction of z. That. Notice that we move this to the right, the left-hand side. Now it'll look very familiar, where z is still between 0 and 1. So do you have an idea what you think the surface of this graph, this function might look like? Jacob?
What's that has to do because of this one?
Yeah, notice this is this equation of a sphere radius 1, but the sphere has to be positive, basically, right? So what we end up getting is the graph of this guy ends up looking like this. We have a nice little hemisphere like that. Is the graph of 3D like a 3D solid, or is it just the surface part? It's just the surface. It's just the surface. The graph should be a two-dimensional thing. Okay. And I think this is what we've been doing, right? All right. Here's where we're going to take it up a notch now. Okay? To have this discussion on dimension. What I want you guys to think about is that another way to think about this is that when z equals 0, you're on the xy plane, right? When z equals 0, you're on the xy plane. What does it look like? How does it intersect the xy plane? When z is 0? Circle. Circle. You can see how it says x squared plus y squared equals 1? Okay. Of radius 1. Okay. So here you have a circle of radius 1. Let's say this is 1 right here. Okay. Where z is 0. What do you guys notice will happen as I increase the z value? What do you think will happen?
Shrinking.
Decreasing radius.
Yeah, notice that this looks like this, right? So as z starts to approach 1, these circles are getting levitated, but they're getting smaller. You guys kind of see that? Okay. You guys ever been to a restaurant and you've seen the tower of onion rings? Okay, it's like there's like a pole, and there's the onion rings that are like stacked on top of it, or inside of it like that. So as z is going from 0 to 1, what's happening is you're having all these smaller circles that are getting stacked on top of each other like this. until eventually, what happens when z is 1?
It's a point.
You just get a point. Okay? So what I want you guys to notice, here, I'm actually going to write it down. As z starts to approach 1, we get a surface which is two-dimensional of a hemisphere by stacking, and this is very informal, okay? By stacking, whatever that means, by stacking circles, which are one-dimensional objects, whose radius, or whose radii, approaches 0. Approaches 0 as z increases. So what I would like you guys to consider is the graph of this function. We can think of it as one-dimensional circles that are getting stacked on top of each other infinitely, because there's an infinite number of them. And as you stack them on top of each other, those one-dimensional circles create a two-dimensional surface, which is the hemisphere. Jacob, yeah.
I guess you could also say that it's kind of like traces in the who is the director or whatever.
Yeah, it's very related to the traces. Very, yeah. Is that cool? Can you guys kind of see that visually? Okay. So then what did we do with a function of two variables? So then we used all this stuff. And then we defined a double integral. We defined this double integral of this particular function, for example. And we said this is going to represent the amount of 3D space between the graph of G and the circle of radius 1, which the circle D of radius 1. On the XY plane. On the XY plane. Where that circle is the circle down here on the XY plane. That's D. We said it's the volume between the graph of the surface, the graph of the function, and this small, not circle, a disk. The disk of radius, the disk, sorry, my English is all bad. The disk D of radius 1. Radius 1 on the XY plane. Sorry, you're using a pen. Apologize. And so what are we calling that? We're saying that this is the volume made. Here's another way I want you to think about this. Okay. That's the volume, right? Inside of here. But now it's including the inside part. Okay? So another way I want you guys to think about the volume is that now let's not picture these as discs, as circles. Picture them as discs. Like now they're filled in inside. And so now this volume, which is three-dimensional space, I can think of it as stacking two-dimensional discs that have area and then just placing them on top of each other. Right? Like, yeah, so it's like now they're filled in. Now they're filled in. And so when you stack them up on top of each other, that entire stack of discs creates the three-dimensional space. And so we have the volume is made from, again, very informal here, stacking. We don't know what that means, but we kind of intuitively can visualize it. Stacking 2D disks on top of each other, where you start with a disk of radius 1, which is the guy at the bottom, D. And then eventually these disks just become a point as you keep stacking. With a disk of radius 1 to a point. So I'm kind of giving you guys a new way of visualizing what's happening. Yeah, Charlie.
So the original graph it's like hollow inside, and now we're filling it up.
Exactly. When you do this here, you're considering the part that's filling it up, the inside stuff. Yeah.
Does the graph doesn't include that circle?
The graph does not include that circle. No.
It just is like
Just hollow inside. Yeah. A bowl, an upside down bowl that's not including the lid. But then the green disc is that lid. Yeah, and that's why it's going to be, that's why it's in between the bowl and the lid. Okay? No.
So like how an integral is the area between a curve and the x-axis.
Mhm.
Would a double integral just be the volume between the curve and the xy plane?
That's exactly right. Yeah. Yep. That's where I'm going. That's where I'm having you guys see that.
But not touching the XY plane.
It does touch the XY plane, but it doesn't. It only touches it at the green boundary of the disk. It doesn't include the stuff inside of it. That's what D is doing. Yeah. Okay. So let's try to do the same thing we did here, but now let's add a new coordinate Z. Okay. Where am I? All right. Let's see what happens now. Let's keep this similar discussion. Hopefully, I don't have to erase much of what I wrote there. And let's see what happens now when I bring in a function of 3 variables. So now, what does the graph of f of x, y, z, and we're going to use this specific example again, 1 minus x squared plus y squared plus z squared, look like? So let's try to figure out first what the graph of it might look like before we start doing volume and all that stuff. Okay. Let's do the same thing we did with this guy. Let's see. So this is going to equal some other 4th dimensional coordinate, which normally we've been labeling as W. Okay. So it's W equals the square root of all this stuff. But similar to the range of this function, notice W is a square root, so it can't be negative. And notice that you have 1 minusing some stuff here, so it's going to have to also be less than 1, less than or equal to 1. So it's still going to have a similar range. Jacob.
Yeah, I was just wondering, how do we actually, like that graph up there on the right with the 2 inputs, like the 2-dimensional graph, so like I'm going to draw 4 dimensions?
We're not going to graph it, but I'm going to have you try to visualize it. Okay, that's fine. I was like, fuck it. I mean, we can do it. I can help you guys. And how are we gonna do it? By a similar analogy with this. Okay. You guys ever watch? Never mind. Okay. Stand and Deliver. Have you guys seen that movie? Oh God. Okay. Highly recommend it. It's a movie about a math teacher in LA. Still. Why? Because I'm a champ. That's what it says. Oh man, you guys really have to watch that movie. Okay, so we square both sides. We square both sides. You haven't seen the movie? Oh, you not wrote it. Basically, we're gonna do the same algebra, okay? So we square both sides and we move everything to one side. We're gonna move this guy over here. X squared plus y squared plus z squared plus w squared, which is a little confusing to see what that's gonna look like. But just like as what we did here, we're gonna minus the w to the other side. Like that. Okay? Where we still have this going from 0 to 1. Okay, so now here's that part. How are we going to visualize all this stuff? Okay? When w is 0, what is this equation going to represent when w is 0? A sphere. But that's the question. Is it filled in, or is it just the surface of the sphere?
The surface.
It's just the surface of the sphere. Similar to when this was 0, this was just the circle. It was not the disk. Right? It just included the boundary of the circle. So when w is 0, this will just include the boundary of the surface, or the boundary of the sphere of radius 1, which is just the surface. Okay? So here's where it's going to get weird, okay? Let's pretend there's this fourth dimensional axis w. Okay? When w is 0, what's the shape that we have?
This is hemisphere.
Hemisphere or the entire sphere? It's going to be the entire sphere. Because this one was limiting z, right? So that's why I kept it up top. But this is limiting w, not z. So in 3D space, that would just be a sphere of radius 1. So we got this sphere like this. That's when z is w. Sorry, when w is 0. What happens as w starts to increase towards 1?
It's a point. The circle's the center of the sphere.
It's getting smaller. Okay? So it's getting smaller. It's getting smaller. It's getting smaller. Getting smaller. 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 Until it equals 1, then we get a point. Okay?
So I guess this is kind of a bad question, but is w basically more of a parameter instead of like a variable?
Here's where I'm going. So what I would like you guys to do is I would like you to picture w, let's pretend it's time. Okay? W represents time, and this says from time 0 to time 1. And I want you to picture a snowball. A big ass, or let's not say a big snowball. A snowball of radius 1 foot. So I guess it is pretty big. It's a big snowball. Okay? At time 0, the snowball has radius 1. But as time goes from, let's say, 0 to 1 hour, what's happening to that snowball? It's melting. It's melting. It's melting until eventually you get to time 1 hour, and then it's just a point. There's nothing there anymore. Okay? We can only see in 3-dimensional space. So at 26 minutes, what are we going to see? You're just going to see the snowball, but at that particular time, right? But if we could see in 4th dimensions, we would see all the snowballs at all the different times. Okay? And we're looking at the surface of the snowball. So at times 0, you got the big surface of the snowball. And then a little second passes by. Now you have this surface of the snowball. So if you could see all those snowballs, what would that create? A filled-in sphere. A filled-in sphere. That's right. Just the way stacking all these curves, which are one-dimensional things, when we can actually see them, or at least pretend we see them in our head, creates a 2-dimensional thing, right? So here we have 2-dimensional surfaces, which are the balls, and they're slowly morphing and then you put all those surfaces together to create a solid ball. But it's not a solid ball in the same time. Okay? Let me show you. In case you're having a hard time, stay. So here's the first example. Here was the hemisphere. Okay? And then when we were thinking of the volume of the hemisphere, we were considering, let me go down to 0. We were considering all these disks that are on top of each other when z goes from 0 to 1. Like that. And it disappears. And then it just keeps going. That's what was creating the volume. Okay, but right now we're only focusing on the graph. So it would just be just the circle part. Okay? So it would just be equality. So right now we're creating the graph of the function in the first one, the g function, by doing all those different circles. Okay? But you guys see, that's a circle at a particular time. Let's pretend now z is time. That's a circle at a particular time. This is a smaller circle at a higher time, right? So what we're trying to do here is we're trying to visualize a sphere, a ball. Let me get rid of the extra term. At a particular time, just the surface of it though. Let me do the, yeah. Just the surface of it. But look, at all those particular times, we can only see the ball, the surface of that ball. But if we can see in 4th dimensions, we would see all of them. So we would create a big fat solid. Okay? Cool. Okay. So now let's try to figure out, okay, so kind of, hopefully maybe you have an idea of what the graph would look like. It's just a big solid composed of all these surfaces that are different times. Already kind of weird. Okay. But now let's see if we can grasp, put our head around what we think the integral of this function will look like. Yeah. Okay, so here's the second question. So what will it mean to integrate this function f of x by z over a solid sphere E of radius 1? Let me put the picture that I had here. Okay. So let's see, it's going to end up being a triple integral over some solid E of my function. But now instead of dA, we're going to see it's going to be dV. Okay. So let's use what we discussed here to maybe like make sense of what it will be. Okay. The space inside here is going to be 3-dimensional space. So we said it's going to be the amount of 3-dimensional space between the graph of the function and the disk that's in the bottom of it. Where you started, right? When z was 0, we had a circle of radius 1. Okay? So what's going to end up happening here is we're going to get the amount of 4D space, whatever that means, space, and whatever between means. Between, if we copy what we said here, it's going to be between what and what? What do you guys think? if we try to copy what we wrote here.
The graph of the f, the s, radius one, and x, y, z.
The graph of f and the solid sphere E of radius 1 in 3D space. We'll just call that 3D space. Okay? Instead of XY plane, the XYZ space. So let's see, what the hell does that mean? Well, the way we visualize volume here is we said, I have a bunch of two-dimensional disks that I'm stacking on top of each other. And then when I did that, all the area of all those disks created the volume. So here, what we're gonna have, you're gonna learn a new word. It's called the hypervolume, which usually in math means any volume greater than 3 dimensions. So the hypervolume made by stacking 3D solid spheres now they're solid, just the way the disks were filled in. 3D spheres, solid spheres, starting from the sphere of radius 1 to a point. So let's digest that a little bit. What was the volume here? You had these disks that you stacked on top of each other, and then the area of all those disks, when you put them on top of each other, created the volume of the space, right? So what's happening here, which is hard to visualize, is you have the snowball that I was showing you guys. Now it's a solid snowball, and it starts with radius 1. That snowball of radius 1 has volume, but then the snowball is melting. At each instant that it's melting, you have a smaller snowball with volume. Add up all those volumes until it gets to a point, that's what we're finding. Just the way we added up all the areas of those disks up to a point, and then that gave us the volume. Right? Charlie.
So checking the 3 solids.
3D, stacking 3D solids. Just like it was this. So conceptually, that's what we're doing, okay? Why am I doing that? Because when I took Calc 3, my professor didn't tell me what the hell was solid. There was like an itch I couldn't scratch. I was like, what am I solving? What does this number mean? So what's gonna happen is, right now I'm keeping it simple with like circles and disks and stuff, right? But in the homework problems, you're gonna have a solid. It could be an ellipsoid. It could be some kind of solid, any solid. And then you're gonna have a function of 3D variables whose graph is also this weird three-dimensional thing. Okay? Adding the volumes, all these three-dimensional volumes between the graph and your solid, that's what we're finding. Adding up all those volumes is going to give us what we're going to call the hypervolume. Okay? All right, so how are we going to do this? Well, let's see. I'm going to use, I think it was you, Noah. I was saying, like, you're bringing it back to Calc 1. So this is what I would like you guys to understand, because now you're in Calc 3. So integration, representation, summary. So maybe that way you guys can see the big picture. Wait, careful. All right. In Calc 1, you learned how to do an integral of some function, dx. Okay? What is the thing you were normally integrating over? What did you write here and here? From A to B, right? But what is that visually? What is A through B? Visually, what kind of object is it? It was a line segment. It was just a curve, right? Like a finite curve. So instead, I'm going to write it like this. What you were integrating over was a closed interval, which is really just a one-dimensional region. And then we took it up and we did a double integral. But now we have two variables. dx represented distance. dA represents area. But we're integrating over two-dimensional regions now. Yeah, and so now we take it up a notch. We're going to define in a little bit what this is. You're going to integrate a function of three variables: distance, area, volume. And now you're integrating over something one-dimensional. Here you integrated over something two-dimensional. So here we're going to have to integrate over something three-dimensional. When you integrated this and you got a positive number, what did that number represent? Area under the curve, right? So it represented area. Area under F, which is a two-dimensional thing. Area is two-dimensional. And then when you did a double integral, but that was giving you a volume under the surface of F. And that's a three-dimensional thing. So here, what will have to happen is that the result is going to represent something called hypervolume, which is like the 4D space. Hypervolume under F, whatever that means. So that's why this is going to be confusing to understand what the answer means. Oh crap, I forgot to unshare my screen.
I recently think I realized like hypervolume is the sum of all the volumes.
Yeah, you can think of it like that. Yeah, so volume is just the sum of a bunch of areas, right? Like we said with the tests. And so yes, hypervolume will be like a sum of a bunch of volumes.
So volume and hypervolume is, I think it's just the same. But hypervolume, like they have all volumes together.
They're all together, correct. Yeah. All right, so let me see. Let me put this over here. All right, so let me show you first the game plan of how we're going to define all this stuff. I'm not going to spend too much time on the construction for this, okay? So just like we did for for double integrals, we started with rectangles. We started with something easy, a rectangle. So what we're going to do is we're going to start with, for a triple integral, before we get to fancy solids, we're going to start with the easiest solid, which is just a box. Okay? Where x will range from some a through b, y will range from some c to d, but now z will range from these two other values, which I think in my notes I'm calling them u and v. Okay? What are we going to do? Well, we're going to partition this box into smaller little boxes, where all the little boxes will have the same volume, delta v. Okay? You partition them in a certain way so that all the x's are partitioned by delta x, all the y's are partitioned so they all have delta y, and all the z's are partitioned so they all have delta z length. So then the volume of all of them will be delta x times delta y times delta z. We grab an arbitrary box, pick a point from it, call that box Bij, get that box, get a point, plug it into the function. It's going to give you depth in the fourth dimension. Okay, so we're going to do a very similar process that we did to double integral. Let me see if I can. Let me do this, guys. Hold on. Let me see if I can label it. Let me bring it down here. Yeah. Okay. Yeah, I can write on this stuff. So let me go like this, and then let me erase this real quick. Erase that. That way you can put that. We're gonna label this a little bit, and then you can put it on your notes on that packet that I gave you guys. Okay. So each of these, each small box has the same volume, delta V, which is going to be composed of delta x times delta y times delta z. These guys right here. Okay. Somewhere in your packet, this B here is going to be, remember we use this notation, this closed interval cross this closed interval. Does that, you guys remember that notation? This means x varies between A and B, y varies between C and D, but now we have z varying between V and U. Or let me match the notes, I did U and V. Sorry. I'm gonna bring this down a little bit. Okay. And then, like I said, for each of these little boxes here, you're gonna grab a point, and we're gonna label it Xijk star, Yijk star, and Zijk star. And this is how we're going to define a triple integral. Triple integral. Because there's 3 coordinates, we're going to end up with 3 different sums. And so we're going to say the triple integral of f over a box B, which is what we labeled here, AB cross CD cross UF. Oh shit, UV. Where did the F come from? Is, we're going to say it's a triple integral over a box, x, y, z, dv. And I'm only going to have you guys write this one time. It's going to be the limit, do 3 sums. I'm going to have you write this once, because there's 3 sums. And let's put f of xijk star, yijk star zich star times delta v. And what we're gonna do, like we did with the rectangles, is the x's, we're gonna partition them. Let's see, let's try to do this right. We're gonna partition the x interval, the AB part, we're gonna partition it into m parts. And so we're gonna have I range from 1 to m. The y interval for this direction, we're gonna partition it into m pieces. So it'll go from j equals 1 to n. And then the z interval, uv, we're going to break that up into L pieces. Okay. And then this L, this N, and this M, L goes to infinity, N goes to infinity, M goes to infinity. All those go to infinity. So you're breaking all these intervals, A, B, C, D, and UV, into an infinite number of segments. And so we're going to say a triple integral is defined to this disgusting sum if the limit exists. So if it does exist, remarks. The first one is if it does exist, you would say x goes from A to B, y goes from C to D, and z goes from U to F of your function. Okay. And then you guys see how these are all going to be scalars for a box? So we're going to be able to use Fubini's theorem. Fubini's theorem will apply. Yeah, John.
Does mean B instead of F?
Shit, I did it again. Yes, thank you. Yeah, it's this guy here. Yeah, so Fubini's theorem applies for box regions, or box solids, should I say. I will definitely not have you do a limit. Okay, Joe, yeah, question.
I was gonna say, for problems like this, with at least one of the intervals always be numbers.
So for all these integrals that you guys are learning, the very last one has to be numbers, so that you can get a number.
Theoretically, it's lines.
That's the next part. Yep, here comes the next part. Okay. I'm slowly preparing you so that we can actually do some problems. Okay, if you guys scroll down, if you guys look down under here, we're gonna go to general regions, general solids. Okay. I'm gonna write this stuff out, but I just want to show you here. You know how a region was of type, there was two types? Why were there two types? Because I can either bound the first coordinate, x, or I can bound the second coordinate, y, by functions. But now how many coordinates do we have to deal with? We have to deal with 3 coordinates. So now there's going to be 3 types of solids. But here's where it gets tricky. For a type 1 solid, E, you're going to bound Z. Okay? So you guys remember the ruler thing that we were doing for regions? Where I was having you guys like look at what's the upper bound and what's the lower bound? Same thing applies. Picture this as a piece of meat. you're cooking, and you poke it with a steak. You're gonna poke it up like that, okay? So when I poke this solid, the lowest bound for that solid is when I poke it going in the z direction. Now it's going to be bounded above by a surface and bounded below by a surface, not a curve anymore. Okay? This same thing. I poke it from the bottom going up, and then it's going to be bounded above by this surface and bounded below by the surface down here. That's a type 1 solid. Oh, yeah.
I guess I just kind of noticed that the inputs increases dramatically as you go on.
What do you mean by the?
Like, you start off with just constants in the outermost integral, and then you have a function of one variable and a function of two variables.
Correct. Why do we have functions of two variables? Because it's a surface, and we need a function of two variables, like what we've been doing in chapter 14. So we have, I'll write over here. We're gonna have 3 types of solids. Type 1. Type 1, I'm just gonna write out what's being bounded. Z is gonna be bounded by a function of x's and y's though. This is gonna become important. A function of x's and y's below, and another function of x's and y's below. Right, because the surface, these are going to be functions of x's and y's, these surfaces. And so what ends up happening is you have your triple integral over your solid E of your function. So this is what you're going to do. You're going to say Z will be bounded below by u1 of xy and bounded above by u2 of xy. dz, like this. You're going to integrate this function in terms of z. So what's going to become the constant now? X's and y's are now constants when you're integrating with respect to z. Okay? So you do this first, and then you're going to deal with the 2 other ones later. Here's where it gets a little harder. This tells you that z, the lowest z will be is this, the lowest z will be is that, okay? Your skewer, let's picture that skewer analogy, okay? I have my skewer right here, poking my surface, but that skewer is now bounded. I can only move it with respect to the region below it. My skewer can't be over here, it can't be over here, it has to be inside of this region. Right? So now what you need to do is you got to say, okay, now what is x and y bounded by? Well, you're going to have to, oh man, this class is crazy. You're going to have to project your solid onto the xy plane. How do we do that? You're going to get these functions and you're going to let z's equal 0. And then see what you can graph on the xy plane. Kind of like what you've already been doing. There's like equations with z's on them and you let them be 0. You do the same thing. You let them be 0, and then you graph them. And then once you graph the region, then you have to say, is this a type 1 region or is this a type 2 region? Like what you've been doing on the homework already. If it's a type 1 region, then y is bounded above by a function of x and bounded below by another function of x. Yeah.
So each type has 2 types of.
Correct. So there's a total of 6 things that you need to consider. First, the type of solid, and then the type of region. Yeah. Is that okay? Okay. I mean, it's not okay. I'm just saying, like, you guys kind of understand what the construction is going to entail? Yeah? Okay, we'll look at an example, okay? Then you do the same thing. You do the same thing, but now if it's bounding X, so if it's a type 2, it's going to bound X. This is why I printed all those packets for you guys, because it's too much drawing. So now notice this has X as the second variable that you're going to integrate, versus this one had Y as the second variable you're going to integrate. Okay? So this is in terms of Z, this is in terms of Y, this is in terms of X, while this one is Z, X, and then Y. That way you can keep track of the order.
So the first variable we have to integrate should be Z. And
For a type 1 solid,
type 1 solid.
because Z is what's being bounded first by these two surfaces.
Okay.
Yeah. So in your notes, if you're writing this part, then what you'll need to do is consider, or no, from here, you're going to project the solid onto, and then this part's important, guys. The solid that you're dealing with is going to be projected into the plane of the two other variables that you still don't know. I already have Z under control, so I'm going to project my solid E onto the plane of the two other variables that I still don't know how to bound it, which means it's the XY plane. Determine if the 2D region is of type 1 or 2. When you get to this part right here, determine if you need to use polar coordinates. It's like all coming together in this section. Meaning, if I, kind of like what we did in 15.3, maybe this region, I don't want to bound X's and Y's, I want to turn it into polar and do R's and thetas. Right? When you get to this part down here, it's basically everything you've been doing so far in the homework. All right, let me go over the next two, and then we'll try a problem, and then we'll take a break. Okay. Does it show? Damn it. No, I want to write on them. I want to write on them. Okay, here's a type 2, I should say solid. A type 2 solid. Which coordinate is being bounded first? What do you guys think from the picture? X. It's gonna be X, okay? So this guy here bounds X. So here, somewhere here on this bad boy here, you're gonna have X being bounded below by a function of Y and Z. Okay, by a function of Y and Z, because X is, you're gonna go towards the direction of the X-axis and put my skewer through here, poke it in this direction now, not up and down. It's bounded below by this function of Z, Y and Z, and it's bounded above by this other function of Y and Z. f of x, y, z, but now you're doing dx first. Okay, here's the other part that's going to be kind of hard. What are the two coordinates that you need to bound now? You need to bound y and z. So you're going to project your solid onto the yz plane. That's how you know that. You see, what are the two coordinates left? YZ. So I have to now project onto the YZ plane. That means what coordinate is 0 on the YZ plane? X, right? So here, to project onto YZ plane, you're going to let x equal 0 instead of z. We'll see. We'll see an example. I just want to have it in your notes. And then for the type 3 solid, that's going to bound y. Bound y first. And so you're going to have y. You're now going to go hook your skewer in the y-axis direction. It'll be bounded below by some function of x and z. And bounded above by another function of x and z. What are the two variables that you need now for this? You're going to need x and z, right? So your solid, you're going to project it onto the xz plane, where y is always 0. Okay? So you're going to project onto the xz plane, let y equal 0 now. No, doozy. Perfect side thing. Yeah. Whew. I think we should take a break first, and then we'll do the example. Okay? Let's do a break. I'll leave all this here. Let's take a break. All right, here we go. Woo! All right, let's try one of these out. We're gonna like really break it apart and spend like all these grids here to help you out. So here's what a homework problem will look like. So evaluate the triple integral where E is the solid bounded by the parabola y equals x squared plus z squared, and plane y equals 4. And this is the interval we're being asked today. Square root equals z squared equals b. Okay. So I'm actually going to use the entire board for this fun. So I want to draw some good pictures here to help you out. All right, let's see. So you're going to want to have a sketch. Now, it doesn't have to be a beautiful artistic piece, but you do want to have some kind of sketch. Let's do it down here. See what it might look like. Okay? So you got this paraboloid here. Let's say you have z being 0. What would the trace of that be? Z is 0. Or what is the shape of that? Parabola. Well, opening towards which axis? Opening towards the y-axis. So it'd be like some parabola kind of going this way, right? What if x was 0? Still parabola. On which plane? The YZ plane. Beautiful. So then notice that the parabola is going to be centered at the origin, but it has to open towards the y direction. So it's going to go like this. And it's telling you it's a paraboloid. Okay? So it's a paraboloid facing that way. And you guys, what is that plane going to look like after y equals 4? Yep, just a big fat sheet of paper that slices it. Check. It's a nice little plane that's slicing it. Yeah. And so this part right here is the solid that they're talking about. This is the solid plane. Are we finding the volume of the solid? Is that what this is asking us to do? No. That's what we're triple integrating over, is this solid. What does that mean? Hypervolume, where the points that we plug into this function, this is the function f of x, y, z. And the points that are plugged here only come from this solid. That's what's happening. We're plugging into some function that has some weird three-dimensional graph somewhere in 4D space. But there's that hypervolume between this solid and that other graph of text. And we're finding its hypervolume. So, exactly. Yeah. But we're not finding the volume of this stuff. We're integrating over it. Because we can't see the over parts. Okay. So what you're going to have to do from here now is I have to say, okay, what kind of solid is this? Is it a solid of type 1, type 2, or type 3? Okay? Just like you guys did with regions, you can have a region that was of type 1 and type 2, right? You could also have a solid that's of several types, or maybe even all the types. Check, yeah. Well, actually, I want to show you that it's actually going to be all 3, but I want you to visually see that. That's where it gets hard. Okay? So it turns out this solid is of all 3 types. And let me show you how you want to start practicing your brain to do this. So if it's of type 1, what I would like you guys to do is, you have your skewer, right? Your stick that you're poking onto this solid, and it's going in the z direction. You're poking it this way. When I poke it this way, I want you to see that there's the top part of the paraboloid, which looks like this. And then there's the bottom part of the paraboloid, which looks like this. Can you see that? I slice it on the xy plane. Yeah. And then I get the top part and I get the bottom part. That means that z, when I poke it up, z is going to be bounded above by this surface and bounded below by the bottom part of the paraboloid surface. Okay. But now the question is, what I'm supposed to be bounding z by 2 functions, right? What are those 2 functions? So if I'm trying to bound z, we have to bound z. The paraboloid is given by this equation. So what are we going to do to this equation to bound z? to help us figure out what these functions are gonna be that bound Z. What do you think? You're gonna have to isolate, where you're gonna use the equation of the paraboloid, but isolate the Z variable. Okay? So to find the bounds, of Z, we're gonna get this equation, and we have to isolate Z. So let's isolate Z. Let's move this over here. And we're gonna get Z is equal to y minus x squared. Then I take the square root, and notice that I get a plus or minus y minus the square root of y minus x squared. So now that we have that, what do you think the top surface is going to be? What's the function of the top surface? Positive square root. And then the bottom one? The negative square root. So that would tell me that that Z is going to be bounded below by the negative square root and above by the positive square root. Okay? Then I'm going to have these two guys. So, but let me start with it. Questions on that part? Can you see it? Okay. Type 1, your first guy here. So we're still using this function. We were given the function here, but now we're doing dz first. So what are the next two variables? X, y. So what are we going to do to this solid? Project it onto the xy plane, but it's a little confusing because it's like on the xy plane, so it doesn't need to project it. Well, it's like you're squishing it, and you're just seeing how is it on the xy plane? What's like its shadow? That's all kind of weird. So what does it mean to do? What are we going to do to this equation then? We're going to make z equals 0, correct? To project it onto the xy plane. So project onto the xy plane by letting z equal 0. But I can graph this one because there's no z, right? Y equals 4. That's right here. That's just this guy right here. That's that line. This is y equals 4. But then this equation, if I let z equals 0, that's going to just be y equals x squared. So that's this parabola right here. Jacob, yeah. You're saying that z equals 0 here?
Or not? As this guy. Or it's because it's separated.
Because I'm separating them, yeah. So that's the tricky part. It's like you're gonna have to like figure out how you use this guy. Here we used it by isolating z and finding the bounds, but here we're using it to project it onto the xy plane and letting z equal 0. This parabola here is the parabola where it intersects the xy plane. Yeah, no. It's given to you. It's given to you. Okay. The homework problem, when it says evaluate the triple integral, it'll just give it. Yeah. Mm-hmm. Yes, Thomas.
So I might have missed something there. In the example, it says that the parabola is y equals x squared plus z squared. So then why is it root x squared plus z squared?
Right here?
No, the actual f of x, y, z.
This guy here?
Yeah, it
Oh.
says y equals x squared plus z squared. square roots of it.
Totally, yeah. This is the function you're integrating. This is telling you what E is going to be.
Oh, okay.
This is helping you find what E is, but this is the function. That's the three-dimensional function that we're using to integrate over this E. Yeah. Yeah, good question. Okay, so you guys get here now, right? You project it onto the XY plane. This is the shape that you get. So now you have to decide, do I want to use my region and make it of type 1, type 2, or do I want to use polar coordinates? That's kind of the next part. Okay. So what do you guys think? Type 1, type 2, or do I want to use polar? Yeah, what's the easiest one to bound? Type 1, right? Type 1. So we're going to do type 1. So I'm going to do type 1, like you guys have been doing in your homework. So now I'm going like this. So therefore, y is going to be bounded below by with a parabola, which is just y equals x squared, and then bounded above by 4. And then as I move that laser going up, it's going to move between which two x values? Yeah, where these two intersect. In order for y to be 4, x has to be 2 or negative 2. So that gives you your bounds. So it looks like we're going to do dy and then dx. And then we start integrating. Okay. Some of the homework problems, though, we'll just have you guys create, like, just stop there. We'll just say, construct the triple integral. So that way. Does that look like it's going to be fun to integrate? Hell no. Okay. The way this looks, you're going to have to use trig substitution. Okay? And then you're going to do that, plug in some more square root stuff. No. So then you probably don't want to do type 1. But I want us to practice type 1. Okay? Just so you guys see, I wanted you to start, this is what I need your brain to start learning to do. Okay? Let's say I want to do type 2. Type 2 bounds which coordinate? It bounds x, right? Okay. So if it bounds x, now you're going to poke the solid towards the x direction. Now it's going like this way. Okay? So instead of having a top and a bottom, you're going to have a front part of the paraboloid and a back part of the paraboloid. Let me see if I can graph it somehow. So it'll look something like this. It's going to look, this is going to be the front part of the paraboloid. And then this is going to be the back part of the paraboloid. You guys can see that? Okay. All right. So now we're not going in the z direction, we're going to go in the x direction. So it's going to go like that. Okay? Well, since we're bounding x, we need to bound x by a function of which two variables? Y and z, right? So we're going to use the paraboloid equation, but now what are we going to isolate? Now we're going to isolate x so that we can get it as an expression of a function of y and z. So to find bounds for x, we're going to get the same paraboloid equation, but now we're going to isolate for x. So minus the z squared, so we get x squared is y minus z squared. So we get plus or minus the square root of y minus z squared. Similar to how we did it here. So therefore, my first integral is going to have x be bounded. Oh, here, let's label it. the back part is x equaling which one? The negative, because it's x is a negative coordinate back there. And then the front part is x with the positive square root. Okay. So x is bounded below by the negative square root. And then bounded above by the positive square root. So what are the next two coordinates that we need to bound? So what are we going to do to the solid? Project it onto which plane? Project it onto the YZ plane. So we're going to have to project onto YZ plane. To do that, we're going to let which coordinate equal 0? We're going to let x equal 0. So I'm going to have the YZ plane. I have this equation, and I have this equation. And I have to graph them on the YZ plane. Y is still equal to 4, that's no biggie. But now it's going to be right here. What does that look like? Just a nice line where y equals 4. So you get something like this. But then now you're going to let, which coordinate did we say we're going to let equal 0? So you're going to let x equal 0. Y equals z squared. Is that going to be a parabola going up and down or opening towards the y-axis? Open towards the y-axis. So let's move over to this. So this is a y equals 0 plus z squared. And notice that now this is your two-dimensional VGP. Okay, so now you figure that out. You see that it's like this weird parabola disc thing. And then you got to figure out which coordinate do I bound next? Do I bound y next or do I bound z next? And so here it's completely up to you. Do you want to bound it going like this or do you want to bound it going like that? Maybe sideways, right? Let's do sideways. So we're going to bound it going sideways. Which coordinate is that bounding? The y-axis, right? So the y variable. So let's see, y is going to be bounded below by the parabola. What's the equation of that parabola? Y equals z squared. And bounded above by y equals 4. And then lastly we have, we have z. It's going to go, yeah, same as like the other one. This is going to be at positive 2, this is going to be at negative 2. Whew. Oh, dy dz. Uh-oh. Integrating that is going to require trig substitution again. And my bounds, again, are really ugly. Okay? We're just practicing, just so you guys see it. But you definitely don't want to do this type. Let's see what happens. Hopefully the third type of solid is nicer. Otherwise, we're kind of F. Let's see. This one's going to bound, let's see, we're down to z, x. It's going to bound y. Let's see what happens when we do that. Okay. Now I go back to my solid. I'm bounding y. I'm gonna go like this. I'm poking the solid in this direction. What is it being bounded below by? When I poke my skewer here, what is it going to be bounded below by? Visually. It's going to be bounded below by the entire paraboloid and bounded above by the disk. So this is a little different from these two scenarios. Here it's being bounded below by the paraboloid and it's being bounded above by the disk. So notice I have something like this now. So then to find the bounds of y, I need to figure out how to write them as functions, right? What is the equation of the paraboloid? You see how y is already isolated? That itself is a hint that you probably want to use that type. Okay? So this is y is equal to x squared plus z squared. And what is this one? What's the equation of that surface? Also, y was isolated. Again, a hint that this is probably the type you want to use. Okay? So to find this guy, notice that I'm noticing that y is going to be bounded below by the paraboloid and bounded above by y equals 4. The algebra is so far way nicer, so I don't have to do all this stuff because this equation already had y by itself. That tells me that that y is going to be bounded below by this function of x's and z's and bounded above by this y equals 4. Let me stop there. Questions on that? Is something you want me to repeat? No, yeah.
Here to be overfillment for this, symmetric because around the to be good on the right.
So the last part, the what?
Like, that's the radius, and like, the distance we do to the graph, we do it like from the y to the graph.
Let me see. Hold on. It might answer your question in the next part. Okay, let me know if it answers your question. Okay. We have these bounds. What are the next two variables? XZ. So what are we going to do to that solid? Project it onto the XZ plane. We're going to project onto the XZ plane by letting y equal 0. We're going to let, what are you going to say? Y is equal to 0. Okay? This is going to be a little weird. Okay? This is where this is going to get a little funky. So sometimes doing this helps out by just putting it here and graphing. But if you guys notice, if I let y equals 0, you can see that that just gives me like a circle of radius 0. Well, that's because it's just giving you the point. But that's not necessarily what we want. We want to project this solid onto this guy here. So notice, what shape would that make if I do that? It's going to make a circle. It's going to make, yeah, this circle here. But that circle is going to be as big as this circle. So the question is, how do I find the equation of that circle on the XZ plane? Exactly. Because notice where the intersection happens, that is where that circle ends up happening. So how do you make these intersect? Substitute the y and a 4 into this equation. Okay? So here this won't help. Or let y equals 4 into the other equation. And so that way you get 4 is equal to x squared plus z squared. And that's going to give you this circle here of radius 2. Okay? Sorry, I'm going to do it. I want to match my other notes. You don't have to erase it. You don't have to erase it. I just want to keep it consistent. Okay. This is now D. That circle is this circle right there. Okay. So here we go. Now you get here and you say type 1, type 2, or do I do polar? It's a circle, right? Let's do polar. But what are you converting into polar? Which coordinates? X and Z, not X and Y. Okay? So what we're going to do is we're going to convert the X, Z coordinates into polar. What does that mean? That means that X is going to equal what? In polar. R cosine theta, but now what equals R sine theta? Z equals R sine theta. Okay? And so what will X squared plus Z squared equal? That's now going to be R squared, exactly. So that's where you're going to have to keep track of all this stuff. Okay? If you were to do, this was to be the ZY plane, Y will equal R cosine theta, which is, we're so used to doing R sine theta for Y, right? But you just got to be careful on the plane that you're at when you're converting to polar. Okay? So if you're converting to polar, R is going to be bounded by what and what? R is going to be bounded by 0 and 2, and theta is going to be bounded by the whole shebang, right? 0 to 2 pi. So let me write it this way. So that means that when you're going to rewrite your triple integral, what is now x squared plus z squared in polar? R squared. Yeah, now that's going to get converted to y equals r squared. This is still a 4. What does the function become? The square root of, this becomes a square root of r squared, which is just r, right? So then this just becomes r now. And what is this is still dy. But what does dA become in polar? R, you got the R right. R dr d theta. So there's an extra R that gets popped out. That we'll have to multiply in here. And then now we have our polar bounds, which are R is equal to 0, R is equal to 2, theta is equal to 0, theta is equal to 2 pi. And so then if I clean this up, theta goes from 0 to 2 pi, pi goes from 0 to 2, y goes from r squared to 4, and then now because that r was extra there, I got to do this. Which I have in the notes. I worked it out in the notes, okay? When you work this out, You're gonna integrate r squared with respect to y. So what is r squared with respect to y? It's just a constant, right? This is gonna be r squared y, and you plug in the bounds. That part I'll leave you guys to. It's moving parts. Okay? It's in the notes though. So you're gonna end up getting, yeah, I'll do one more step. 0 to 2 pi. R goes from 0 to 2. This you're gonna integrate r squared y, plug in the bounds. Yeah, you get 4r squared minus r to the 4th. dr dθ. Finish this up, and you end up with 64/15 as your answer. But notice that the integration is way easier than both of these. Say it again. Oh shit, there's a pi. All right. Yeah, totally. This one? Or this one? That was it right there. Yeah, thank you. So when you're doing your homework, here's my tip. You see how all the equations have y being isolated? That probably means they want you to do a type that has that variable being bounded. Okay? As you saw, it turns out to be the easiest one. Remember, this answer does not give you the volume of that parabola. It gives you some funky, weird hypervolume from the graph of this function, and like between that and this 3D solid. Okay, that's about okay, these are rough. Okay, so it's the first day. So what I'm going to do is I have a solid that's given to you here. Okay, and I gave you one possible way of constructing the triple integral. I would like you to find the other 5 ways of bounding. Okay? So I need you to practice that. I don't care about the integration right now. I care about your knowledge of bounding. So here's the solid. One way that it's bounded. I want you guys to find 5 other ways that it's bounded. Okay? Don't do the back just yet. The back, I have one more comment and then I'll explain the back. Because this part's going to take a while. I'm just the messenger, guys. Don't hate me, okay? I'm just the messenger. Hopefully, it's going to help us out. Imagine doing this part of class asynchronous. Yeah, I'll take the extras, guys. All right, let's see. Do you guys usually work together? YouTube, have you together? YouTube, have you Let me put this guy's grade. go around and help you out. Notice, guys, the integral is giving you dz first, which means that you're bounding z first. Okay?
There's five other ones, yeah, there's DZ and then DXY.
Yeah, I'll write them out. So you're given, I think this is the one you're given, right? So then you have to find this. You're gonna have to find. This is what I meant, guys. This is the one you're given. You have to do 5 other triple integrals so that they're in this order with the correct balance. I'll help you out. I won't help you out. What you might need to do is sketch these 2D regions to help you out. So if you're going to do this, right? You're going to do this one. You see how the last two are x and y? So what you're going to want to do is figure out what is the region in the x1 going to look like in the picture. Correct, and then you're going to actually have to figure out the equation for it. So there's another so this one, yeah, it goes like this. So now that you have the region, that's the x-axis, this is the y-axis. They already did this one. You're gonna do this one. You're gonna bound x first. Let's just switch these. Do that. You're gonna want x going this way. You better write this equation by isolating x. You're going to do x and y. The dz would still be the same. Now it's like x and y. So what you're going to want to do is figure out how can this, if I could project this into xy plane, what will that do? Correct.
Easy,
The way that it's drawn is this, so you can go here, draw coordinates. What is this equation? Kind of like what I was saying here, you need to project this, you need to see, can you graph this? How can you graph this one? Okay, so you see. No, that's what I'm saying here, right? No, that's it. Right, one half. And then, right. Is it ten on the orientation? So here the x-axis is this person.
Now the other one's like easier to get the other type because you already have.
Yeah, you just care about how can I rewrite this equation? So then basically, what I like to do is rewrite this, and now we can put it back.
Okay, so you said the Z stays the same. Okay.
This one is those guys. And here's
We can, if you not, no, or should I do this? Correct, yes. Are you going to actually for projection of x, y? Okay, so that was already done. You have to find the equation. Yeah, all those.
of the projection of the triangle.
The equations are different because you have to find the terms of x.
Yeah.
Yeah.
Oh, like the projector? Yeah, so here, this is one of those where.
Yeah, it's just this.
But it's kind of like this one when we try to project it. Like we could have just let we couldn't just let y equal 0, because then we just got a point. So we have to figure out where the intersection is. So here, you want to so you see this intersection between there? That's the curve.
So then why is it that? It's a rotation. That's it. And then I see this one X equals the Y equals 0.
So how are we going to find the if you do that, it doesn't give you any of this curve. You want to see how this curve looks like.
Oh, the diagonal. No, because the Y equals root X.
We write the Y.
Curve on X, Y.
Is a square root.
When you're projecting the X onto it's, you have to find
Let's see how that
this edge right here, which is a combination of Y equals root X and this one on Y. So you plug in root X and Y, and it's equals 1 to X.
So
In terms of X and form of let's just look at those two.
what about
How would this be? Because first of all, this one. For this one? Yeah, for this one. Yeah. So maybe for X.
equals 0? It's 0, right? Let's go a little higher. There we go, perfect. That's what I mean. So you see
Okay.
Yeah, I mean, I think like I want to learn.
Yeah. So
This would be put up onto the X. I mean the
Yeah, no, I just.
we have Z first, so we want to put X in terms of Z. Just kind of ignoring Y, right? That's why we kind of switch it onto the X, Y, and X, Z. All we gotta do is we gotta take all these lines here and just like squish them on. And so one way that you could do that is by getting rid of the variable that like makes it go out. The variable that makes it
your
go
Z
out.
bound, you're still doing the Z. So it doesn't matter.
Oh, why? Okay, no, you're right.
So doing that.
Or did you plug in X towards there?
Yeah, you could do it that way. And you put it there, is equal to 1 minus X squared.
I'm almost thinking this one really
You
counts
add
for
it to the side to get it.
Subtract 0.
Square both sides.
He said not to do it yet.
I guess that's. That was the moment.
Yeah.
Yeah, you buy X.
Because it's on the X. And then it's like, they're like unrelated. Yeah. But because you're putting them in the same. Like I did here, look at this and just see like.
I got white
Switch it down. It's the X.
At least you get it for
Switch it to Y. Let's just do that. I mean, this one, it's just very squishy. The Y.
I guess you could.
One minus Y is equal to Y. And then the X ones are.
X on the outside.
like
When you look at the Z minus one. That's the actual like function. The negative root x.
Yeah, because that's how x is increasing, that's how the x variable is. So we only use the.
You guys should do engineering.
I just find it works.
Whatever the interval is. Find two things you're using.
Okay. X
I struggle. The classes I'm taking
I mean, yeah, but similar. So we added y.
It won't always be. This example, this equation. Like here, right?
So,
Like when I isolated the variable, Jacob, these all look very different. So we can't always assume that nice property. Because that's the equation that has all three of them.
It'll go out like
this one, yeah. My true view is weird because it's very hard to yeah, you can't visualize what it represents. I like
So remember when
especially when it's like
that's the part I'm going to mention that in a little bit. But remember that we learned that this
that's actually kind of what
just gave you the area of this region.
So this will do.
Volume. It's just the function one. Yeah.
Imagine it as.
How's it going? I already have my solutions here.
All those. Yeah. But then it's like this function here, so like that doesn't graph this. This is just the plan. That's just the stuff. That's like you're really functions. Like this could be the function for a sphere. So what does it mean for it to have a sphere integrated over this self-function? It'd be like how much of the area lines like that?
yeah, you might I wrote all my like
Sphere, it's one, we're adding that.
This one right here? 이제 거야 지금. Looks like it's well, remember that the square root function looks like this, right? So when you negate it, now it's going to look like that. When you put a negative, it flips it over. And then you add 1 to it, it shifts it.
High-dimensional thing. You gotta imagine that.
All right, guys, you guys can start. Some of you guys are getting farther into it. You guys can check right here, okay? This will be on the notes, the PDF that's posted on Canvas. You guys can check. So this one is kind of what I was telling you. Yeah, let me erase it. So for the XZ plane one, you're going to intersect the two functions that are on the surface. So I believe you get this right here. Remember that the square root function looks like this. So then you negate the square root function. So now it looks like this. And then you're shifting it by 1 up. So it looks like this. Or it depends, because you're on the XZ plane. Where this is z equals 1 minus vx. So if you want to bound x will be bounded by 0, and then you have to isolate x for this one. Yeah, so you have to do 1 minus z, and then square both sides. All right, guys. We got 15 minutes left. Perfect. Just the last piece. Last part of the section, and then we're done. Now you guys know why I need to cover 15.5 really fast on Tuesday. I need as much time as I can for this section. Okay, for the back part. The back part is a property of triple integrals, so I want to just cover that real quick. Sure. All right, so the last part. Oops. So let's just kind of bring it back now, and let me remind you of something. Triple integrals and volume. Recall that in the previous sections for this chapter, we found that when you double integrate the function 1 over a region, you guys remember what that gave us? When you double integrate it over a region D? Just gave you the area of the region D. Okay? Because this just means Z equals 1. So you have like this prism of height 1. The volume is 1 times the area of the base, which is equal to the area of the base. Okay? And so we get a similar property for triple integrals. Now, when you have a solid E and you triple integrate over it, and your function is just a function 1, what do you guys think that's gonna equal? It's gonna equal the volume of the solid. But be careful, okay? That's when you're triple integrating the function 1. Triple integrating the function 1. If this triple integral does not have the number 1, you're not finding volume. You're finding hypervolume. It's just the hypervolume when this equals 1 is 1 in the 4th dimension times the volume of E. 1 times the volume of E is just the volume of E. Okay? And so notice if E is a type 1 solid, where Z is bounded below by 0 and some function f of xy. Let me show you a picture here. So let's say it's some solid, something like this. And you got a solid like this. So you have some solids like that, right? Someone has their, it's a little too loud. And you're bounding Z, and it's a type 1. So we're gonna do what I had you guys practice. Okay, this is your solid E. But if it's a type 1 where this solid has Z bounded by 0 to f of xy, where this is f of xy right here, I want you guys to notice the following. If I use what this tells us here, the volume of E, I triple integrate the function 1 over this solid of this particular type. What are the bounds for Z? What is Z bounded by here? It's bounded by 0 below, and it's bounded by f of xy above. What's the antiderivative of 1 with respect to Z? What is it? It's just Z, right? From 0 to f of xy. So notice that this just ends up being what you guys learned before, right? We learned that to find the volume between the xy plane and the graph of a function f, the surface, gives you the volume, right? But notice that that's just really what this is saying. Triple integral where Z is bounded by 0 to f. So it's telling you the same story, but in different ways. Okay? So it's just a nice little fact to kind of see that everything we've been saying is agreeing with each other. Like both of those are telling you the same thing. When your solid of the volume of the solid you're finding is between the xy plane and 0. And the graph of that. This right here is the definition from 15.2. That's how we define the volume of a solid between F and the xy plane. All right, and so I just wanted to highlight some applications of triple integrals. this class used to be, DVC used to have 18-week semester classes. And then 2018, I believe, the district changed everything to 16 weeks. And so we used to have like 2 more weeks of time to cover stuff. So there were usually more applications covered in this class. Now it's like professors have to basically remove anything that was not required and stick to what is required, which hella sucked because it was cool to see some applications. One is similar to what we've been doing, which is average value. Average value. So the average output of f of x, y, z over a solid is 1 over something, the triple integral of the function, dv. We were doing 1 over the area, but now what do you think we're going to do since we're dealing with a solid? Volume. So like you have some solid and you plug in points from that solid and it gives you temperature. Let's go back to temperature. Okay. Doing this will give you the average temperature throughout the entire solid. Okay. Your application now. If you're doing physics, you might see some of this stuff. You might do triple integrals because in physics, triple integrals are used to find the mass or center of mass of solids you end up taking any of classes where you have to learn electrical charge, that's also it's used for that. Also used to find the electrical charge of solids. Electrical charge of solids. When I taught this in 18 weeks, I wasn't too much in physics. I did more of the next part, which is probability. So I did some of my research in probability. So in probability, triple integrals are used to find the probability of an event, with 3 random variables, with 3 what's called random variables. 3 parameters, like 3 possible things that are affecting the probability. That's what I focused on. So this is stuff you might end up using if you guys are going to do some applied math. Okay. Most folks have to take this and use this in physics. And they see that a lot there. Yeah, we're 2 minutes early. That's it. That's 15.6, guys. We're done.